All right, I heard a beep. I'll begin. Heavenly Father, we thank you for this day. I thank you for these students. And this time we have together, I just pray that you'd be glorified in what we do, Lord. In your name I pray. Amen. All right, against my better judgment, I'm going to do an example like one of your homework problems. Just to make it clear what I'm talking about. So one of your homework problems, I've asked you to work out basically the squared function to prove it's complex differentiable in two different ways. I'm going to do the same, but for the, you guys pick. You want me to do the reciprocal function or the cube function? Reciprocal. All right. So f of z is 1 over z. So that's the reciprocal function. And so in order to, why did I agree to this? No, I reject I reject that choice. I'm replacing it with a cube, as that would be infinitely more helpful to your homework. I'll put the reciprocal on the test. So let's see here. That was a joke. Let's see here. F prime, or was it, of z is, by the definition given in problem 21, also known as the standard definition of differentiability of a complex function. All right. You just take the limit of the difference quotient, which we can write as f of z plus h minus f of z divided by h, right? And complex numbers are a field, so that division makes sense. Yay! And so you just got to, calculus 1, FOIL that thing out. You got yourself z cubed plus 3z squared h plus 3zh squared plus h cubed minus z cubed, all divided by h, right? And so some beautiful things happen. The z cubes cancel, right? The z cubes, they be canceling. And what are you left with? Oh, look at that. You got an h, you got an h, you got an h, you got lots of h's. So you can factor an h out of the terms I just underlined, and this simplifies to what? 3z squared plus 3zh plus h squared, right? So I'm just using, at the moment I've just used algebra, right? Now I'm going to use some limit laws. But anyway, the point is that this does what? So limit laws essentially say, well, that's going to go to 0. That's going to go to 0. This is just a constant with respect to h. So the answer here is 3z squared. So therefore, d dz of z cubed is equal to 3z squared. So that's how we would show that the cube function is complex differentiable using the difference quotient definition. You should recognize this calculation. This is just calculus 1 with a z instead of an x, right? No big deal. Now the other way to do this would be the Cauchy-Riemann approach. The Cauchy-Riemann approach, what would that look like? Well, we'd say, well, my f of z is x plus iy cubed, right? And so what's that work out to? Well, x plus iy times x squared minus y squared plus 2ixy. We've seen that one before. And just multiply this thing out, distribute. You got yourself an x cubed minus xy squared minus 2xy squared, yeah? Plus I times, y times x squared minus y squared. Don't question the order of my distribution. There's no particular order to it. I just do stuff until I feel like I've got everything. At some point, I count my chickens and see if they're as many as I started with. I mean, we've got a binomial times a trinomial. That means 2 times 3 is 6 total terms. Do I have 6 total terms? 1, 2, 3, 4, 5, 6. Yes, I have 6 terms. Everything's there as long as I didn't repeat. And then I just, simplify stuff. What I'm trying to tell you guys is do algebra. All right. Take a breath. I'm trying to relax, right? So you got yourself a 3x squared y minus y cubed. At which point it is manifestly clear what the component functions are of my complex function, right? This is my u, this is my v, right? So at this point I'm like, okay, so f equals to u plus iv, and u and v are continuously differentiable, right? Is that clear? In fact, it's clear. They're continuously differentiable everywhere. They're polynomials. Polynomials are everywhere continuously differentiable. Woohoo. And also, we can calculate ux is equal to 3x squared minus 3y squared. And vx is equal to 6xy. And what else do we got here? uy is what? Looks like minus 3x, oh, minus 6xy, yeah? And what's vy? Vy, got 3x squared minus 3y squared. Hence what? Hence I say, the last time. Hence, ux is equal to vy, and vx is equal to minus uy, which is to say what? The Cauchy-Riemann equations hold, right? F equal to u plus iv is complex differentiable on C. In fact, what do we say when the function's complex differentiable on the whole complex plane? We say the function is entire. This is an entire function. Moreover, we know more, right? df dz is what? It is nothing more than partial f partial x in this case, in this context, because the identity is the first component, so the algebra derivative is just partial f partial x, and partial f partial x here is 3x squared minus 3y squared plus I times 3x squared minus 3y squared, yeah. Although I feel like I just did, oh no, I'm wrong. Come on. This is what? What is this? This is ux plus ivx, right? Is that vx? No. That's not vx. That's a typo. What's vx? 6xy. And then, if you tilt your head and squint, you can see that this is actually 3 times x squared minus y squared plus 2ixy, which you should recognize as being the z squared function. And so we get 3z squared. This is the part A and B that I want you to go through for the square function for your homework, but I just did it for the cube function for you guys here. All right? Let's do another example of this, except this time I'm not going to do the limit part. I'm just going to do the Cauchy-Riemann part. All right? So we could think about log z. How do we define log z? Right, a natural log of the absolute value of z, right? Plus I times the principal argument of z. And this is going to be for z in the slit complex plane C minus, which is also known as C minus the ray from minus infinity to 0. Right, here's a picture. Why do we have to remove this? We have to remove that because that's where there's a jump from minus pi to pi in the angle function, right? One of the things I've included in your homework is a proof, short proof that if we have real differentiable, that implies continuous, right? So if we want a function which is complex differentiable, we need to avoid discontinuities in the function, because if it's complex differentiable, it's certainly not going to be discontinuous, right? So we have to avoid that angle jump if we want to talk about differentiation. That's why we're looking at the slit complex plane, even though technically we've defined the principal logarithm on the whole plane with just the origin removed, all right, to be fussy. Okay, so then in order to apply the Cauchy-Riemann equations, this idea, we need to identify what are the component functions of a logarithm. So what are they? So this is, for z equal x plus iy, we've got natural log of the square root of x squared plus y squared, right? Plus I times, I'll say the argument of x plus iy for the moment. So let's assume that the real part of z is greater than 0, hence the argument of x plus iy is given by what? Yeah, inverse tangent of y over x will work for us because we're in quadrants 1 or 4, right? Where that's the standard angle. And so, apparently, log of z is 1/2 natural log of x squared plus y squared plus I times the inverse tangent of y over x, right? And so there's my real component of f. There's my imaginary component of f. I'm saying that this is f, right? And you can check that the Cauchy-Riemann equations hold for u and for v, right? A little bit fussier here, but some partial derivatives. Ux is 1/2 times what? Times 2x over x squared plus y squared. Also known as x over x squared plus y squared. What's Vx? Well, let's say what's Vy. Vy is, 1 over 1 plus y over x squared times partial y of y over x. What is that? Well, that's y. Oh, excuse me. That's 1 over x times 1 plus y over x quantity squared, or y squared over x squared, which we can clean up, multiply by x over x, we get x over x squared plus y squared, which of course is equal to ux, right? Similar calculations show straightforward partial differentiation. You can show that uy is equal to minus vx, right? And that's true provided that the denominator there is non-zero, which it is non-zero if we're in where? Away from the origin, right? So certainly the Cauchy-Riemann equations hold for the principal logarithm for where real is positive. How would you calculate the principal argument anywhere else around, though? If you think about it, how do you calculate standard angles? You could always calculate the inverse tangent of y over x, right? And either add pi or subtract pi. It's just a shift in angle, right? So we're just talking about adding some fixed constant to get the angle function in other quadrants. So the differentiation is just the same. So even though I've specialized it to quadrants 1 and 4 just for the sake of clarity, if you think about it, the partial differentiation works just the same for the other two quadrants, right? Which proves then the Cauchy-Riemann equations hold on the slit complex plane. Consequently, this function, the principal logarithm, is what we say it's holomorphic on the slit complex plane, which is to say that it's complex differentiable on this open connected set. So because u and v are continuously differentiable and satisfy CR equations on the slit complex plane, we find that, f of z equals to the principal logarithm is holomorphic on the slit complex plane. Okay. Now this is one I don't want to try. I definitely do not want to go back and try to do it this way. Right? Are you guys with me? Do you want to do it this way? No. Do you want to do sine and cosine this way? No. Do you want to do the exponential this way? No. Right? So this is just a starting point in the standard discussion, which we want to get to the Cauchy-Riemann equations because they're a much better way to look at the possible complex differentiability of a function on the complex plane. Any questions about all this? I hope this helps alleviate perhaps some of the confusion of the past few days, because I've been doing things that are much more general than this, and I hope this helps. All right. So there are three things I want to share with you today about the importance of a function being complex differentiable. All right. So what does complex differentiability get for us, right? What does the existence of f prime of z naught mean? All right. There are three different answers. Well, the first is actually not so much that question. It's related, but fine, fair enough. So tied to this, there's three discussions I want to have with you today. First of all, it tells us about local invertibility of f of z. In other words, if I set w equals to f of z naught, right? Well, w equals to f of z for z close to z naught, can I solve for w? Can I solve for z, right? It has an answer for us, a pretty easy answer for that question, all right? It also tells us something about, so that's one of the things, there's section 7.3 on inverse mappings and the Jacobian. That's one thing I want to talk about. It says something, and this is easier to understand, it says f equals to u plus iv has harmonic u and v, all right? That's another thing its existence mean. It says that the component functions are harmonic functions. All right. And then finally, it says that f is a conformal map. It says all of these things. Now, actually, honestly, for both the upper and the lower cloud, what do you want to call these things? Bubbles, clouds, whatever, thought bubbles. Both this and that have fine print attached, but the fine print is pretty benign. It's just that f prime of z naught is non-zero. And this guy, again, we need that f prime of z naught is not equal to 0. So three different questions we can settle. If we have complex differentiability of a function, if that derivative is non-zero, it turns out that that implies that you can find a local inverse for the function. Do you guys know what I mean by local inverse? Maybe you haven't thought about that. Let's talk about that for a minute. Yeah.
Specifically complex differentiability for local inverse, or is it weaker condition like for standard differentiability?
Well, we are focused on complex differentiability here. So when I write f prime of z naught, I'm saying we have a function from c to c, which is complex differentiable at z naught.
Right, but is that, do you need that, or do you just need, like, it would be differentiability?
Oh, we could do with less if we were in advanced calculus, sure. Yeah. In fact, my proof actually involves advanced calculus. All right. Actually, I think I should come back to the first thought bubble because that's the most complicated one. We should start with these two because those are easier. Let's start with those, okay? First of all, the middle one. What does harmonic mean? So definition, a function is harmonic if it solves Laplace's equation. Which Laplace's equation? It's, I guess it's nabla squared phi equals to 0. So the concept of a harmonic function is more general than complex variables, like the Laplacian in 3 dimensions is ux squared, is like the second partial derivative of x with y and z added together, summed to 0. But for complex, for us, I mean, in particular, we have either like uxx plus uyy equals to 0, like that, or we could talk about fxx plus fyy equal to 0. I mean, I'd like to say that the definition of harmonic function could either apply to a real valued function or to a complex valued function. All right. So the theorem is simply this. Theorem, if f is, complex differentiable. Let me try to use the language holomorphic here. If f is holomorphic, on domain D, then fxx plus fyy equals to 0, and the same is true for the real part of f, which we call u usually, and the imaginary part of f, which we typically call v. Now, I showed you guys a way to derive this by a theorem which I'm excited about in a calculus, right? But I'm now going to show you the standard cut and dried complex analysis proof. Here it is. Suppose f is holomorphic. And I think our symbol for that was this kind of like snake that doesn't quite come back on itself of D. So suppose f is an element of the holomorphic functions on D. That's what that symbol, that says f is holomorphic on D. You don't have to write out the sentence, right? You can write that symbol that says f is holomorphic on D. Then what do we know? We know that the y derivative is equal to what? I times the x derivative, right? Those are the Cauchy-Riemann equations. Thus, what happens if you differentiate that with respect to y? What's partial yf? Y is equal to partial y of I fx. But by laws of partial differentiation, we could just rewrite that as fyy equals to what? Well, to be clear, it's partial squared f, well, I times partial squared f, partial y, partial x, right? But remember, partial derivatives commute. And that's still true for complex valued functions. Right? And what do we have? We've got I, partial x of partial f, partial y. What is partial f, partial y, though? It's, I times partial f, partial x, right? These are the Cauchy-Riemann equations. And then you can pull the I out. You've got I squared, which is what? -1. And so that's minus fxx, right? So therefore, fxx plus fyy equals to 0. And the fact that the component functions solve it is pretty much immediate from the definition of how we partial differentiate a complex valued function, right? Like, what's the definition of partial f partial x? By definition, that is partial u partial x, right? Plus I times partial v partial x. So this implies that uxx plus, uyy equals to 0, and vxx plus vyy equals to 0. So 2 for the price of 1. If we have a harmonic complex valued function, we get a pair of harmonic real functions for the real and imaginary part of the complex function. That's how it goes. Now, a little bit more language. When f equals to u plus iv, we say, v is the harmonic conjugate of u. You could also say, but it's just also the imaginary part of that complex function. Yes, true. But it is also the harmonic conjugate of u. In other words, well, there's a more general concept here, which is that, maybe I've said it the wrong way. I've said it the wrong way. I'm sorry. Let me say it in a way which makes this more exciting. Given harmonic u, in other words, uxx plus uyy equals to what? On some domain D, yeah? So harmonic u on some domain D. Then v, solving vxx plus vyy equals to 0, is a harmonic conjugate of u, provided what? F equals to u plus iv is holomorphic on D. Which is just a way of me saying that f is a complex differentiable function on the domain. So this is the definition of harmonic conjugate. So a pretty standard homework question, test question, whatever kind of question you want to think about here is, given a harmonic function, calculate the harmonic conjugate. There's 2 different plans of attack when you're asked this question. The one is just to try to kind of back solve the Cauchy-Riemann equations directly. All right. The other is just to try to think about, okay, what's Cook up to? This is just the real component of such and such function. So the imaginary component's blah, therefore that's the conjugate. Right? I mean, there's rather than saying that, let me show you by example. If I told you u equals to x squared minus y squared is a given function and it's harmonic, right? If this is a harmonic function on the plane, isn't it? Agree? Twice differentiate it, what do you get with respect to x? 2. Twice differentiate with respect to y. Minus 2. So 2 minus 2, 0. Harmonic. Great. So to find the harmonic conjugate, to find v, the harmonic conjugate, the is the wrong word, a harmonic conjugate, we would need to solve ux equals to vy, and also uy equal to vx. That's not quite right. You guys tell me what's wrong about it. Right. So I need to put a minus in there somewhere, right? Which one was it? This one, right? Or let's put it over here, yeah, because the u's are given. So basically, we're trying to solve partial v, partial y equals to 2, and partial v, partial x equals to minus 2. So you do the same thing you do in calculus 3, right? You can integrate both of them, like partially integrate them with respect to x and y respectively, add constants, which are possibly functions of the other variable. Partial integration tells me that that says that the v is equal to 2y plus some c1, which is possibly a function of x, right? Then I can take that, right, and I can plug it in here, and I get partial c1 partial x equals to 2. Wait a minute. I did something wrong. I'm sorry. Let me just. I don't need to do that. I could just integrate both and kind of look at them and play the matching game. This says v is equal to what? Minus 2x plus c2, which is possibly some function of y, right? So if you tilt your head and squint, you can see that v should be what? Yeah. So you said v is equal to 2y minus 2x. That feels very, very wrong to me. Should 2 and minus 2 go there? No. Is that ux? No. Ux is what? 2x, yes. And what's vx is, excuse me, uy is minus 2. So this is actually plus 2y, right? Yeah? Because the minus, yeah? So when I integrate that, I should have 2xy, yeah? And when I integrate this with respect to x, I get 2xy. And so when you compare these two formulas, you see that the constant 1 and constant 2 must in fact just be plain old garden variety constant. So this suggests that we have simply v is equal to 2xy plus some constant. Those are my choices. Those are the possible choices for the harmonic conjugate of u, right? And since we've just shown that by constructing v in that way, it satisfies the Cauchy-Riemann equations, it's continuously differentiable, consequently f equals u plus iv is complex differentiable, which goes back to show that it is in fact the harmonic conjugate. All right? Now, what's the other way of doing this? The other way of doing this is going, f of z equals z squared is x squared minus y squared plus 2ixy. So thus, v equals to 2xy is harmonic conjugate of u equals to x squared minus y squared. Solution. So if you can see what I've given you is the known component function of a known function, you're done. You just write down the other component to it. That's it. And of course, we can always add any constant because that differentiates away. Much in the same way when we calculate potential energy in calculus 3, or a potential function, there's always an ambiguity of like where you set the potential to be 0. You can always add a constant. It still works. Same thing goes on here. Any questions? Like, here's an example. If I told you that well, I'll keep it easy. Suppose I told you that the natural log of the square root of x squared plus y squared was a harmonic function on the slit complex plane, right? And I said, find the harmonic conjugate. You'd be like, it's the, well, that would only work on the quadrants 1 and 2, right? So I should really say argument of x plus iy. Argument of x plus iy is a nice notation for all the whole deal except for the deleted axis, right? So that's our notation. This is our notation for the extension of an inverse tangent to the other quadrants as appropriate, according to the standard angle. Anyway. So there's that. So conformal mapping, what does conformal mapping mean? Do you guys know? So my takeaway message from what I just told you is that there is a deep and interesting connection between solution to Laplace's equation and complex functions. They are hitting at the same thing, and we'll be able to use complex functions to solve Laplace's equation a little bit later in this course. This is what conformal mapping is about. Conformal mapping is a technique to solve Laplace's equation on sneaky domains using complex differentiable functions. So the next thing I'm going to talk about is the conformal mapping idea. So here it is. If I have, two curves, like so, and they meet, their tangent vectors meet and say at angle theta, and suppose this is in the z-plane, then to say the mapping is conformal, F is a conformal mapping, means that over here, the corresponding image curves, like here. So let's see here. We could talk about the domain T, and so we could think about these parametrically, by gamma 1 or gamma 2. Gamma 1, gamma 2 being the parameterization of paths in the complex plane. So a typical point up here would be something like gamma 1 of t, right? Maybe down here we'd have gamma 2 of t. Z equals to that, z equals to that. Those would be paths in the complex plane parameterized by gamma 1 and gamma 2 respectively. Over here, we could look at, this one would be something like f of gamma 1 of t. That would be w. And this point down here would be like f of gamma 2 of t equals to w. So this is the image of the given pair of curves in the target space for f, where w is equal to f of z, our usual notation. This is the w plane over here. So what it means for these mappings to be conformal is that the angle between the intersecting paths is preserved under the map. So like the length of the tangent vectors could change, but the angle between the intersecting curves should stay the same for a conformal map. So that theta, let me call this theta 1, this theta 2. Conformal just means theta 1 equals to theta 2 in this situation. All right. So the reason that a mapping F, which is complex differentiable, has this conformal properties is as follows. If we differentiate with respect to t, f of gamma of t. All right, so basically I'm saying let z equals to gamma of t. So we're looking at a path. We're looking at ddt of f of gamma of t. Then there's a chain rule, and the chain rule simply says this, that this is df dz, that's the complex derivative. You evaluate it at the path, gamma of t, and then you multiply by d gamma dt. And this multiplication I just wrote down is a complex multiplication. All right, this is the chain rule. So this we can prove. Maybe I'll prove it for you guys some other day. I mean, I've given you a proof that's general for A calculus before this. So anyway, what does this say? Well, this says that basically we've got f prime of gamma of t, right? Times d gamma dt. So if without loss of generality, we can suppose that the intersection point happens at t equals to 0 for both curves. You can always reparameterize them so that happens just by shifting the parameter. So that's no loss of generality there. So t equals to 0. On the one hand, we can look at gamma 1 prime of 0 dot gamma 2 prime of 0, right? That would be equal to what? The length of gamma 1 prime of 0 times the length of gamma 2 prime of 0 times the cosine of theta 1. But on the other hand, we have what? We have that f prime of gamma 1 of 0 times gamma prime 1 of 0 dot f prime of, oh my goodness, so much to write here. I wish I had a, goodness gracious. Oh, fine, it is what it is. F prime of gamma 1 of 0 times gamma prime 1 of 0. That vector dotted with the same but with 2's. Well, that defines angle theta 2, right? So, listen, I'm going to call this thing Pac-Man 1. I'm going to call this thing Pac-Man 2. So we'd have the length of Pac-Man 1, gamma 1 prime of 0, times the length of Pac-Man 2, gamma 2 prime of 0, times the cosine of theta 2. All right. We don't need to do too much more writing to see the point. There's a formula for the dot product as it relates to complex multiplication. Do you guys remember what it was? If I take the vector v and I dot product it with the vector w, that's equal to what? The real part of what? Say again? VW bar. So this is a formula for the dot product of two-dimensional vectors in the complex plane in terms of just a complex multiplication, right? So let's see here. Trying to think of a notation that will help you process this. Can't see, sorry. Ah. This is not that hard to understand, but it's horrible to write out in my current notation. I have chosen poorly. What I'm trying to get to, guys, is that when you actually calculate like cosine theta 1 and cosine theta 2, it works out to the same thing. Because what ends up happening is like you have the length of, you have basically the modulus of Pac-Man 1, the modulus of Pac-Man 2, both appearing in the length functions on this side and in the dot product over here. So when you sort through this definition as it applies to this, the complex derivative itself, the magnitude of that cancels out in the denominator and the numerator of the fraction which defines cosine theta 2. And it leaves you with the same fraction that defines cosine theta 1, which gives you equality of the angles. What's needed to make that cancellation, though, is that the derivative is non-zero. If the derivative is non-zero, then the modulus is non-zero, so the cancellation makes sense. And consequently, we get that the angle between two intersecting paths for a complex function is the same before and after the map. That's the conformal property of a complex differentiable function. I have that here. I'll show you a second. Oh no, not this chapter. I did some proper name calling here, which was to essentially point out that, I mean, and there's something additional in my notes which points out that the tangent vector to the new curve, really, when you look at it, this formula right here, so this is a complex number, right? At the point, this is f prime of gamma of 0. So in other words, f prime of z naught, the point of intersection of the curves, that's just some radius r times some angle e to the I theta. So what that does to the tangent vector geometrically is it rescales it and it rotates it by theta like that. So it makes a lot of sense that we'd have conformal, right? Because you're doing the same thing to both vectors. You're scaling and rotating, but you're doing it in the same way, and that's why we have conformal. But the formal proof is just that the dot products, the cosine defining the ratio of the dot product, this is the notation for dot product, of the lengths is the same before and after, because it's just this, I get the rescaling, the length of the e to the I theta is just 1, so it doesn't change anything. And anyway, this is the proof. I'm sorry, I wish I had longer to belabor it, but I don't. Work through this for yourself, please. You trying? So the theorem is just this. If we have the derivative is non-zero at a point, then f is conformal at that point. All right. Let me actually show you what that means, though. All right. So f of z equals z squared, right? We can look at the mapping t maps to t squared minus y naught squared plus 2i y naught t. What's that? That's the path which says x equals to t and y is fixed, right? So that's a horizontal path, right? I was trying to relax today. Somehow, oh, I know what it was. I did a homework problem for you guys at the start of class. It messed up my plan. You forgive me for that. This is a horizontal path in the xy plane. This is a vertical path in the xy plane. See, because and then, well, this is actually not an xy. This is the image of the horizontal or vertical path in the xy plane to the w equals z squared through the square map. And when you look at what this is u equals to t squared minus y naught squared and v equals to that, which is in fact a parabola. So what this calculation shows you is that the horizontal vertical grid in the xy plane gets mapped to like parabolas under the square map as it happens. This is just the nitty-gritty of it, but here's a picture. What we're looking at are the paths that, this is what the image of the rectangular grid of the xy plane looks like in the w plane. What is the angle between the xy coordinate lines and the z plane? 90 degrees, right? And as you can see, the image of those gives these parabolas, which also meet at 90 degrees in the uv plane. W equals uv plane. So there's that conformality. That, by the way, is actually a link to this. You can click on that and play with that yourself, copy it, do whatever. The other, of course, you could also look at it as u equal to a constant, v equals to constant. Look at the rectangular grid in the uv plane and see what it maps back to, because in fact it goes the other way. If f prime of z naught is non-zero, then so is its the other way around. Anyway, so this is actually the inverse image of the rectangular grid in the uv plane back into the xy plane. And again, you get this, except for one point, right? There's that one point in the middle, which is where z equal to 0, which your homework will show f prime of z squared is, derivative of z squared is 2z, yeah? So where is that 0? The origin. The origin is the one point where this mapping is not conformal. Here's some pictures of the exponential. Again, you see these beautiful orthogonal trajectories, if you will. Yeah. So there's really something really neat to discover about how complex functions take a rectangular grid of coordinates and map them to a curvilinear, but still orthogonal grid of coordinates, as long as the derivative is non-zero. There's all kinds of interesting coordinate transformations to see in these complex functions. Yeah? So that's one of the things a complex function is. Admittedly, I have neglected the first thing, which is to talk about local invertibility, so I'll try to come back to that next time. I'm sorry, guys. That's actually important because there we discover another way to understand another way to calculate the derivative of the logarithm. Oh, I've erased it. What did I forget to do for the derivative of the logarithm? I forgot to emphasize to you what is ddz of log z equal to. This is what we'll show next time. I bet you guys could already tell me. I mean, you're like, well, it was ux plus ivx, right? But if you look at that, that was x minus iy over x squared plus y squared, given calculations I didn't quite finish. Sorry. What's that? This is 1 over z. This is not surprising. The derivative of the logarithm is the reciprocal function. My second example today shows that, but we can look at it from another perspective. How did we find it in Calculus 1? What was the way we looked at it? Remember? Implicit differentiation. So we should talk a little bit about why implicit differentiation still makes sense in the complex case. So that's still an important technique of finding derivatives and understanding them. All right, I'll shut up. Thanks, guys. Got it?